take omega FP. Let's look at the finite probability space where omega is the 0, 1 to the 3. So it's the elements of this omega are lists of length 3, which with binary entries. So omega k belongs to 0 and 1. Let's take F to be the power set because that's what we can do without worries in the finite setting and countable setting as well. This is supposed to be number 3. Okay, so let's define probabilities using this. I'm defining now the probability of every element of or all the indicator sets. So let's make a table. We have omega there, and then we tell what is the probability of each of these singleton sets. And if I I'm taking out the commas, so I just write the entries like 3 lists. So we have these binary things. And how many events we have? We have 8. So 1, 1, 0 and 1, 1, 1. These are now all the 8 elements of the probability space. And then I'm assigning probability 1, 4 to this. And then I'm assigning zeros here and 1, 4 to this. 0, 1 fourth, 1 fourth, and then nothing there. So with this table, I'm defining the probability measure now. And the essential elements are here and there, there, and there. These are the elements with non-zero probability of them. And let's define xk of omega. I'm defining 3 random variables. I'm defining this as omega k for k equals 1, 2, and 3. Okay. And now the question is, now we have 3 random variables, x1, x2, and x3. Are these random variables independent or not? So my question is, actually, let's change k into j, because we have become used to the j to be indexing now this collection. So let's say xj is omega j for j equals 1, 2, 3. I'm asking now, is collection xj, j from 1 to 3, is this independent? That's my question. And if you look at this setting, so now we have defined everything. So we should be able to answer this question. To study this, we could, for example, what we could do. There are of course many ways to look at this, but one way is to look at, let's define event ek to be the pre-image of. Sorry, again, I'm confusing with j and k. Let's say ej is the pre-image of 1 for random variable j, and these are now events, measurable sets. So we ask, okay, what's probability of E1 and E2 and E3? Let's look at what's the probability of all these things. So to understand this, we need to look, okay, what is E1 actually? So what is the set of omegas for which x1 is equal to 1? So that means set of omegas here for which the first coordinate is 1. And we look at this is the last 4 elements. So we find that E1 is actually the collection of these 100, 101, 110, and 111. That's the entries with first coordinate 1. Then we could look at what's the entries with second coordinate 1. So these are, if we read from the table, so it's this this, and this, and then the third one is the entries with last coordinate 1, so we can write it down explicitly. And then we could see, okay, what's the intersection of these? So then if we read from these, E1 intersection E2 intersection E3, it's the set of omegas for which every coordinate is equal to 1. So it contains only one element, 1, 1, 1. Yeah. And so that's why the probability of this joint event is the probability of the singleton set, which only contains one entry, namely the sequence 1, 1, 1. The probability of 1, 1, 1 is 0. So we find that, okay, this is 0. But what is the probability of E1? If we read from the table, what's the probability of E1? So the probability of entries with 1 at the first coordinate. So these are the non-zero entries. So let's highlight them in this way. These are the non-zero entries still. So we look at from these entries, which of them have coordinate first coordinate 1? It's these 2, and then we sum up these 1, 4 plus 1, 4. So this is 1/2. Yep. Same way, the probability of E2. We can calculate these all probabilities. And actually, if we look at from the table, we see that all of these are equal to 1/2. So we conclude that this is 0, but then the product probability of E1 times probability of E2 times probability of E3 is equal to 1/8 if we multiply these. So it's 1/8. So we conclude that we found 3 events in this sigma algebra. So we found that we have E1 in the sigma algebra of x1. We found E2 in the sigma algebra of x2. We found E3 in the sigma algebra of x3. And we found that the probability of the joint event E1 intersection E2 intersection E3 is not equal to the product of these. So these are not independent. Yeah. So our conclusion is no. Do you agree with me? Clear enough, hopefully. Okay. What is special about this example? This table is well chosen table in the sense that there's something special in this. If you study this table in more detail, so we could note some properties. For example, actually here in this table, you can verify that x1 and x2 they are independent. So if you only look x1 and x2, you can do this, verify that x1 and x2 they are independent. You can verify that x1 and x3 are independent. And you can verify that x2 and x3 are independent. So there's lots of independence in this collection, but jointly x1, x2, and x3, they are not independent. So it's an example to highlight it. This example, the message is that pairwise independence does not imply independence. Let's say mutual independence of everything. In the same way as pairwise correlations, maybe you have seen in basic courses, pairwise correlations do not imply the full independence or lack of pairwise correlations. Okay, that's the message here. What other message there could be? Actually, we might have defined this table. We might define this that, okay, in this case, what was the intuition building this table was that x1 and x2 are independent coin flips. I would say they are coin flips. So in the sense that both give 1 with probability 1/2 and for case equal to 1 and 2. And then x3 is actually here kind of a parity. So x3, you can check that is actually x1 plus x2 modulo 2. Or if you like logic, you could think 0 means false, 1 means true. So in this sense, this is the XOR operations of x1 logically and x2 logically. So you could actually write this in your favorite software, maybe Python or R, and you could write this XOR command for these random variables. You generate 2 independent coin flips, and then you do XOR for x3. So this is kind of your parity bit. If you look at the table, so in all of these red entries, so if I have false, false, so then the third bit is false. I have false and true, so then I have XOR, so it means true. True and false, XOR gives me true, and true, true, XOR, exclusive OR gives me false in this case. So that's why kind of the parity bit is dependent on the first 2 bits intuitively. But if we only look at the first bit and then the third bit, so then they are still mutually independent in this example. All right, I think this is an example that tells you kind of what independence means in a finite setting, and everything kind of generalizes, works in infinite spaces as well.